First, I wanted to thanks Google's team and Kaggle's team for this amazing competition. It was a pleasure to actually work on it. I'm happy to get the second place, to be in the prizes. So our team is named Latenciaga, and we're gonna go with the standard agenda. But first, I'll tell a couple of words about the team. So my name is Dmitry Hizbulin. I'm the team lead. Currently, I'm a applied AML engineer lead at KAUST. I work with Professor David Pugh, and other team members are from all over the place. Denis Devitsky is a research engineer. Ivan Saev is VP engineering, and our software engineer Kirill Snezhko. Right, so we are diverse, like geographically and in terms of experience, also diverse team. Why the name? Name is basically latency. By Latenciaga becomes Latenciaga. So latency, I believe it's another name for runtime, quite frequently used. Going straight to the solution. The solution is a graph neural network trained on A100. Luckily, we have access to the latest GPUs. It's a seemingly classical PyTorch plus torch geometric, and the setup is training each collection separately. So training is quite heavy, 20 hours each collection. In terms of feature engineering, so the concept was to come up with the best fit standard solution for this problem, and then to go deeper into the rabbit hole of fine-tuning everything, including like working out how to use features better. Basically, the feature processing flow was very simple. So the same as the first place, we removed the duplicates by config values. We took the minimum, not random, out of them. For determinism, we removed some graphs which we think are damaged. Actually, we removed only several of them, even though we spotted some problems with data with many of them. So engineering-wise, it was important to repack data so that so we can get random access to the configs. And with feature values, we didn't do anything apart from getting them through this compression function. It's a very nice compression function, which just basically logarithming values that supports negative values. It nicely compresses those, like adds up, and yeah, sums and products of values. They don't overshoot the range anymore, since they are basically logged. The graph neural network, I would say it's absolutely basic neural network, basic graph neural network, just a stack of 6 or 8 SageConv layers. We also experimented with GetV2 and several other layers, and all of them either worked worse or didn't work at all. We tried to keep the sizes of the size of the model small. So since it acts as a regularization for the training. So the convolutional network is self-regularized, and the small model also has this nice effect. I know that's a good practice is to have a big model and apply regularization techniques to actually improve generalization. But here, like augmentation is not available, basically. Dropout didn't work for us like this. So we had to actually keep the model small. We organized the batch in a hierarchical way. So the lower level of hierarchy is what we call a micro batch. It's basically the same as the first place. So we take one graph, we sample several configs out of it. Yeah, and within this micro batch, or also it's called the slate in ranking, I think. We were simply different configs, but we also could also don't stop on at this stage, and we actually batch up multiple graphs in a extra dimension, which is like a normal batch. So the total batch size for layouts that we managed to fit into 80 gigs of astonishing 80 gigs of A100 is 40. So since we had access to high-end GPUs, we kind of didn't think about even pruning the graphs which could drop the accuracy of the network potentially. So we were able to fit 40 networks, so to say, 40 samples into one batch, and we work with quite small micro batch sizes. So basically, the numbers of configs, either 4 or XLA or 10 to NLP collections. And we train with in this manner. So in terms of like training scheduling, everything is quite basic. AMW, quite high learning rate, lots of iterations, step scheduler, and yeah, as I mentioned, it takes 20 hours, and it was not the fastest cycle that we tried to train the model. Without any early stopping, just taking the value from the last iteration. The most peculiar thing is the losses, and this is a ranking problem. And ranking is a little bit partially new to us, so we had some exposure to it. Nevertheless, the losses are, there is an abundance of flavors of losses for ranking, and there is no clear winner. What we did is we went with listmle for layout collections, and we kind of came up with our own loss, which is basically a margin ranking loss, which operates on all the combinations of predictions and targets, which we dub diffmat loss. And let's take a look how it works. So it basically takes the predictions and builds the matrix of all of the differences of all predictions between each other. So it's like an anti-symmetric matrix, and we only need the upper triangle or lower triangle. as unique values. We repeat the same for targets, and now we have a vector of differences, and now we can feed them into the marginal ranking loss. The second value, we feed 0. Right, so I'm not sure how much scientific novelty is there, but we discovered that it actually worked better than ListMLE. So for XLA collection. So XLA collections are relatively small. There is a significant domain gap between train and validation, or between train val and test. So this setup seemingly gave us a little bit better generalization. So we went with it for XLA collections. Right. So one thing that probably helped us to stand apart from the competitors, except for maybe first place. But we tried to make a like an inherited generalized solution, no probing, no hacking, no trying to pick up good runs almost for the public dates, for the public leaderboard, and it helped us to move up from the actually silver medals to the second place on the private leaderboard. Right. So that's what would we do if we were like designing the solution for production. Yeah. So findings, interesting findings, simple thing. Ranking loss is very important. Element-wise loss doesn't do the thing. As I mentioned, the layout dataset, sorry, XLA dataset is quite small, and regularization was needed. Yeah, I would propose a different different metrics for scoring. So maybe they weighted average over speed up and Kaggle tau, and and Kaggle tau, of course, it's especially for the default data sets. It's not a very good metric in the sense that lots of values of configs, runtimes for different configs are very close and close to the best, but the measurements themselves are noisy. Like, so I measured it as 0.4% of span. Probably it's not even that important for finding those super good configs if they are only like 0.4% better, nevertheless. And one important thing with the data that, so we basically do the EDA in a little bit different format, in the sense that we plotted runtimes over the config ID. And for example, for some graphs, we have, like, normally we have 100,000 configs and 100,000 runtimes for the datasets. And we see that the distribution, so we expect the distribution is the same over configs, because kind of we are sampling from the same distribution, even though it is like not Gaussian, multimodal. But here we see different workers probably. So Paul mentioned that 20 workers were benchmarking in parallel. And since that they were benchmarking sometimes different stuff, maybe different graphs, maybe just data got like aggregated from different actually graphs, or I don't know, maybe something with random number initialization. But this is the most outrageous kind of example. Others are more subtle, like here for muscular CNN, we see that it just jumps like this, and it's kind of not important if we are talking about like differences or absolute values, but for ranking, it's very important. So like we don't get 100% Kendall Tau and don't even get close to it, probably because of because ranking is super sensitive to the noise, and yeah, and we can't rank noisy stuff very good, seemingly, like this. So I try to eliminate algorithmically those measurements which don't kind of fit the general trend by using entropy function between adjacent blocks of 100 samples. It was detecting something, but the results of training with this filtered dataset were no better than the baseline. So we decided not to go with this filtration. But it's kind of, yeah, for the task at hand, it is not helpful. Better just figure out how to improve the data collection and generate the dataset. And one thing that we also try to do is actually map between test and train val, and figure out what is there actually in the test. And we kind of found it by cross-correlating the histograms of operators. So operators, even though we don't know where's the convolutions, where the concatenations, they have their IDs. I can build a histogram, and some matches are exact like here. Relation is perfect. We see that for some reason, for XLA, we have 2 efficient nets in test. So there is some bias towards efficient net. But the experiment with actually oversampling what is there in the test and like undersampling everything else, it didn't go well. There was no improvement, and we decided to leave the to leave the proportions of the graphs in the datasets as they are, and not use this information of the composition of the test.